Simulated annealing is a probabilistic technique for approximating the global optimum of a given function. Specifically, it is a metaheuristic to approximate global optimization in a large search space. It is often used when the search space is discrete, for problems where finding the precise global optimum is less important than finding an acceptable local optimum in a fixed amount of time. Simulated annealing may be preferable to alternatives such as brute force search or gradient descent. The name and inspiration come from annealing in metallurgy, a technique involving heating and controlled cooling of a material to increase the size of its crystals and reduce defects. Both are attributes of the material that depend on its thermodynamic free energy. Heating and cooling the material affects both the temperature and the thermodynamic free energy, while the same amount of cooling brings the same decrease in temperature. The rate of cooling dictates the magnitude of decrease in the thermodynamic free energy, with slower cooling producing a bigger decrease. Simulated annealing interprets slow cooling as a slow decrease in the probability of accepting worse solutions as it explores the solution space. Accepting worse solutions is a fundamental property of metaheuristics because it allows for a more extensive search for the optimal solution. The method was independently described by Scott Kirkpatrick, Daniel Gellert and Mario P. Becky in 1983, and by Vlado Cerny in 1985. The method is an adaptation of the Metropolis-Hastings algorithm, a Monte Carlo method to generate sample states of a thermodynamic system, invented by M.N. Rosenbluth and published by N. Metropolis al. in 1953. Overview. The state of some physical systems, and the function E to be minimized is analogous to the internal energy of the system in that state. The goal is to bring the system from an arbitrary initial state to a state with the minimum possible energy. The basic iteration at each step, the SAR heuristic, considers some neighboring state S of the current state S, and probabilistically decides between moving the system to state S or staying in state S. These probabilities ultimately lead the system to move to states of lower energy. Typically, this step is repeated until the system reaches a state that is good enough for the application, or until her given computation budget has been exhausted. The neighbors of a state. The neighbors of a state are new states of the problem that are produced after altering a given state in some well-defined way. For example, in the traveling salesman problem, each state is typically defined as a permutation of the cities to be visited. The neighbors of a state are the set of permutations that are produced, for example, by reversing the order of any two successive cities. The well-defined way in which the states are altered in order to find neighboring states is called a move, and different moves give different sets of neighboring states. These moves usually result in minimal alterations of the last state, as the previous example depicts. In order to help the algorithm keep the better parts of the solution and change only the worse parts. In the traveling salesman problem, the parts of the solution are the city connections. Searching for neighbors of a state is fundamental to optimization because the final solution will come after a tour of successive neighbors. Simple heuristics move by finding best neighbor after best neighbor and stop when they have reached a solution which has no neighbors that are better solutions. The problem with this approach is that the neighbors of a state are not guaranteed to contain any of the existing better solutions. This means that failure to find a better solution among them does not guarantee that no better solution exists. This is why the best solution found by such algorithms is called a local optimum, in contrast with the actual best solution, which is called a global optimum. Metaheuristics use the neighbors of a solution as a way to explore the solution's space, and although they prefer better neighbors, they also accept worse neighbors in order to avoid getting stuck in local optima. If the algorithm were run for an infinite amount of time, the global optimum would be found. Acceptance probabilities. The probability of making the transition from the current state to a candidate new state is specified by an acceptance probability function that depends on the energies of the two states, and on a global time-varying parameter called the temperature. States with a smaller energy are better than those with a greater energy. The probability function must be positive even when is greater than. This feature prevents the method from becoming stuck at a local minimum that is worse than the global one. When tends to 0, the probability must tend to 0 if and to a positive value otherwise. For sufficiently small values of the system will then increasingly favor moves that go downhill, and avoid those that go uphill, with the procedure reduces to the greedy algorithm, which makes only the downhill transitions. In the original description of SAR, the probability was equal to 1 when, i.e., the procedure always moved downhill when it found a way to do so, irrespective of the temperature. Many descriptions and implementations of SAR still take this condition as part of the method's definition. However, this condition is not essential for the method to work. The function is usually chosen so that the probability of accepting a move decreases when the difference increases, that is, small uphill moves are more likely than large ones. However, this requirement is not strictly necessary, provided that the above requirements are met. Given these properties, the temperature plays a crucial role in controlling the evolution of the state of the system with regard to its sensitivity to the variations of system energies. To be precise, for a large, the evolution of is sensitive to coarser energy variations, while it is sensitive to finer energy variations when is small. The annealing schedule, the name and inspiration of the algorithm, demand an interesting feature related to the temperature variation to be embedded in the operational characteristics of the algorithm. This necessitates a gradual reduction of the temperature as the simulation proceeds. The algorithm starts initially with set to a high value, and then it is decreased at each step following some annealing schedule, which may be specified by the user, but must end with towards the end of the allotted time budget. In this way, the system is expected to wander initially towards a broad region of the search space containing good solutions, ignoring small features of the energy function, then drift towards low-energy regions that become narrower and narrower, and finally move downhill. According to the steepest descent heuristic, for any given finite problem, the probability that the simulated annealing algorithm terminates with the global optimal solution approaches 1 as the annealing schedule is extended. This theoretical result, however, is not particularly helpful, since the time required to ensure a significant probability of success will usually exceed the time required for a complete search of the solution space. Pseudocode. The following pseudocode presents the simulated annealing heuristic as described above. It starts from a state S0 and continues to either a maximum of kmax steps or until a state with an energy of mn or less is found. In the process, the call neighbor should generate a randomly chosen neighbor of a given state S. The call random should pick then return a value in the range 0, 1, uniformly at random. The annealing schedule is defined by the call temperature, which should yield the temperature to use, given the fraction r of the time budget that has been expended so far. Let S equals S0. For k equals 0 through k max. T temperature, pick a random neighbor, SNU neighbor if P, E, T, random, move to the new state, S SNU. Output, the final state S. Selecting the parameters. In order to apply the SAR method to a specific problem, one must specify the following parameters: the state space, the energy function E, the acceptance probability function P, and initial temperature less than initial temp greater than. These choices could have a significant impact on the method's effectiveness. Unfortunately, there are no choices of these parameters that will be good for all problems, and there is no general way to find the best choices for a given problem. The following sections give some general guidelines. Diameter of the search graph. Simulated annealing may be modeled as a random walk on a search graph, whose vertices are all possible states, and whose edges are the candidate moves. An essential requirement for the neighbor in the traveling salesman example above, for instance, the search space for cities has equals 2432902008176640000 states, yet the neighbor generator function that swaps two consecutive cities can get from any state to any other state in at most steps. Transition probabilities to investigate the behavior of simulated annealing on a particular problem. It can be useful to consider the transition probabilities that result from the various design choices made in the implementation of the algorithm. For each edge of the search graph, the transition probability is defined as the probability that the SAR algorithm will move to state when its current state is. This probability depends on the current temperature as specified by temp function, and on the acceptance probability function P. Acceptance probabilities the specification of neighbor and temperature for many problems, and adjust the other two functions according to the specific problem. In the formulation of the method by Kirkpatrick al., the acceptance probability function was defined as 1 if, and otherwise. This formula was superficially justified by analogy with the transitions of a physical system. It corresponds to the Metropolis-Hastings algorithm. In the case where t equals 1 and the proposal distribution of Metropolis-Hastings is symmetric. However, this acceptance probability is often used for simulated annealing even when the neighbor. One must consider that after a few iterations of the SAR algorithm, the current state is expected to have much lower energy than a random state. Therefore, as a general rule, one should skew the generator towards candidate moves where the energy of the destination state is likely to be similar to that of the current state. This heuristic tends to exclude very good candidate moves as well as very bad ones. However, the former are usually much less common than the latter, so the heuristic is generally quite effective. In the traveling salesman problem above, for example, swapping two consecutive cities in a low-energy tour is expected to have a modest effect on its energy, whereas swapping two arbitrary cities is far more likely to increase its length than to decrease it. Thus, the consecutive swap neighbor generator is expected to perform better than the arbitrary swap one, even though the latter could provide a somewhat shorter path to the optimum. A more precise statement of the heuristic is that one should try first candidate states for which is large. For the standard acceptance function above, it means that is on the order of or less. Thus, in the traveling salesman example above, one could use a neighbor. One must also try to reduce the number of deep, local minima, states that have much lower energy than all its neighboring states. Such close catchment basins of the energy function may trap the SAR algorithm with high probability and for a very long time. As a rule, it is impossible to design a candidate generator that will satisfy this goal and also prioritize candidates with similar energy. On the other hand, one can often vastly improve the efficiency of SAR by relatively simple changes to the generator. In the traveling salesman problem, for instance, it is not hard to exhibit two tours with nearly equal lengths, such that is optimal. Every sequence of city pair swaps that converts to goes through tours that are much longer than both, and can be transformed into by flipping a set of consecutive cities. In this example, and lie in different, deep basins, if the generator performs only random pair swaps, but they will be in the same basin if the generator performs random segment flips. Cooling schedule. The physical analogy that is used to justify SAR assumes that the cooling rate is low enough for the probability distribution of the current state to be near thermodynamic equilibrium at all times. Unfortunately, the relaxation time, the time one must wait for the equilibrium to be restored after a change in temperature, strongly depends on the topography of the energy function and on the current temperature. In the SAR algorithm, the relaxation time also depends on the candidate generator, in a very complicated way. Note that all these parameters are usually provided as black box functions to the SAR algorithm. Therefore, the ideal cooling rate cannot be determined beforehand, and should be empirically adjusted for each problem. Adaptive simulated annealing algorithms address this problem by connecting the cooling schedule to the search progress restarts. Sometimes it is better to move back to a solution that was significantly better rather than always moving from the current state. This process is called restarting of simulated annealing. To do this, we set S and E to S best and E best and perhaps restart the annealing schedule. The decision to restart could be based on several criteria. Notable among these include restarting based on a fixed number of steps, based on whether the current energy is too high compared to the best energy obtained so far, restarting randomly, etc. Related methods. Interacting metropolis hasting algorithms combined simulated annealing moves with an acceptance rejection of the best fitted individuals equipped with an interacting recycling mechanism. Quantum annealing uses quantum fluctuations instead of thermal fluctuations to get through high but thin barriers in the target function. Stochastic tunneling attempts to overcome the increasing difficulty simulated annealing runs have in escaping from local minima as the temperature decreases. By tunneling through barriers, taboo search normally moves to neighboring states of lower energy, but will take uphill moves when it finds itself stuck in a local minimum, and avoid cycles by keeping the taboo list of solutions already seen. Dual-phase evolution is a family of algorithms and processes that mediate between local and global search by exploiting phase changes in the search space. Reactive search optimization focuses on combining machine learning with optimization. By adding an internal feedback loop to self-tune the free parameters of an algorithm to the characteristics of the problem, of the instance, and of the local situation around the current solution. Stochastic gradient descent runs many greedy searches from random initial locations. Genetic algorithms maintain a pool of solutions rather than just one. New candidate solutions are generated not only by mutation, but also by recombination of two solutions from the pool. Probabilistic criteria, similar to those used in SAR, are used to select the candidates for mutation or combination, and for discarding excess solutions from the pool. Graduated optimization digressively smooths the target function while optimizing. Ant colony optimization uses many ants to traverse the solution space and find locally productive areas. The cross-entropy method generates candidate solutions via a parameterized probability distribution. The parameters are updated via cross-entropy minimization, so as to generate better samples in the next iteration. Harmony search mimics musicians in improvisation process where each musician plays a note for finding a best harmony altogether. Stochastic optimization is an umbrella set of methods that includes simulated annealing and numerous other approaches. Particle swarm optimization is an algorithm modeled on swarm intelligence that finds a solution to an optimization problem in a search space, or model and predict social behavior in the presence of objectives. The runner route algorithm is a metaheuristic optimization algorithm for solving unimodal and multimodal problems inspired by the runners and routes of plants in nature. Intelligent water drops, which mimics the behavior of natural water drops to solve optimization problems. Parallel tempering is a simulation of model copies at different temperatures to overcome the potential barriers.